Number one, which one has more entropy, a gas more than a liquid? I guess this one has more atoms in there than that one, so maybe you could say that. I think C is worth skipping. Aqueous is more spread around than solid for sure. This has more gas molecules. That's an increase in entropy. More gas molecules is an increase. 3 and 3 gas molecules is kind of a wash. Solid to aqueous is an increase in entropy. Gas to solid is a decrease. And aqueous to solid is a decrease. On 3, I don't know where this table is, but what you'd have to do is do products minus reactants. But notice you'd have to do this one times 2, this one times 3, this one times 2, and so forth. That's where they get these numbers here. And then you would get S standard, entropy standard, delta S standard, because you're using the S standard formation values for the chemicals. And when you string them all together, you get the delta S standard for the reaction. Not the way you're using it individually, but the standard version if you run it a mole of times. On 4, delta H is a positive and delta S is a negative. And since we're going to take negative of a negative, what we have is a positive plus a positive, and it must be a positive. There's no logical mathematical way out of that. And so it is spontaneous in the reverse only, not in the forward. And they didn't ask about the reverse, so there are no conditions, no temperatures for which this version is thermodynamically favorable. On B, they want to use an inequality, and that is kind of a more elegant way to do it. And then I have a different version. So if I want this to be favorable, I want delta G to be less than 0. And since this is the equivalent of delta G, I'll set it less than 0, which means I can do this. I can pull the delta H standard over and put in the values, and I solve for T is less than 620 K. So if T is less than 620 Kelvin, then the delta ST term in this equation will let delta G be negative, which means the reaction is thermodynamically favorable. Again, not at all times, only at temperatures less than 620 Kelvin. Now, here's another version where you just set the whole thing to 0 and put in the numbers. Now, why would I do that? Because I'm always a little bit afraid that I'm going to miss a trick and divide by a negative on an inequality and not notice. So it doesn't matter. You can pick either one. We're going to get the same answers. If I set it to 0, I can pull this over as a positive, divide, and I get 620 equals T. Now, the trick to this one, I admit, is deciding should you be over or above 620. And then you have to go back and do a little math logic. I want a negative, and since this is going to be a positive, I need this to be lower in value. I need this to be a small value, not a very large value. A very small value would do me better than a very large value. That means that I'm going to want T to be below 620 Kelvin. Below 620 gives negative delta G. On C, we have basically the same problem, and you can do it their way again, or sort of my way, so to speak, and just use the logic that in this case, I want this to be a large value inside here so that I get a greater negative than that is a positive. A much higher temperature does me much better than a much lower temperature. So when I find the breakover point, so to speak, I want T to be greater than that Kelvin. And that produces a negative in delta G. That goes negative for delta G. For D, both the delta H and the delta S are performing in the way that makes the overall reaction thermodynamically favorable. That's a negative, that's a positive, so it doesn't matter what the temperature is. At all temperatures, delta G is negative, and the reaction is thermodynamically favorable. On 5, this does get a little bit more complicated, and they give a big hint here, and they even write out the reaction. Of course, the evaporation is one molecule going from liquid to gas. So what we have then is a way to assemble the delta H standard, the delta S standard for the reaction, because we can do products minus reactants for both delta H and delta S, and that's what they're doing here. And then we have the overall statement for the reaction, delta S standard, delta H standard, and we can put them into the delta G. Now, again, in this case, they've set it lower than 0. Since this is delta G equivalent, I want delta G to be less than 0. Solve, and we get T is less than 336. In this case, it's arguable that the setting it to 0 method actually works a little bit better because they want the boiling point. And this way you find out the exact boiling point. Of course, it doesn't really exactly matter, but you could solve for 336. And that, of course, that should be Kelvin, shouldn't it? Is equal to T. I would play around with the Lewis dot diagrams and make sure that you can generate those. Those are not very complicated, and you are expected to be able to do those kinds of diagrams. Not only ammonia, but say any carbon chain that has N with 3 covalent bonds, and you're expected to know that that unshared valence pair is a good point for proton acceptance. In B, they give this delta G standard for the certain temperature being discussed. And of course, that's per mole of reactions. And so what's going to come really key here is that if we run this reaction a mole of times, we're going to need 3 of those. Or if you knew the moles of this, you would run the reaction 1/3 as many times. And that's the way this is going to come up. We're going to take our grams, convert to moles of H2. The reaction will run 1/3 as many times as what you found here. And then that's a certain percentage of a mole. And then it would be that percentage of this many kilojoules. And it turns out that it's actually over 100%, isn't it? Because in this case, it is possible to have, say, more than 100%. We could run this reaction 100 moles of times, theoretically, even. If delta H is a negative number, then energy has come out of this reaction as it proceeds to the right, which means that nature has created a more stable set of bonds. So this set of chemicals is less energetic than this set. It has less potential energy, and the bonds are more stable. It has lower potential energy and stronger bonds. And they do think that you know that, and it probably will come up. That also means that the bond dissociation energy is larger. It'd take more energy to break this up than that. It goes hand in hand with the top line there. Delta S standard is a negative. Well, that does stand to reason quite a lot because we have 4 gas molecules turning into 2 gas molecules. So the disorder of the universe has been reduced. For the formation of ammonia, delta H is a negative, and so is delta S. Now, that's what nature likes in this case, and is what nature doesn't like in this case. Since this is a negative, and we're going to have to reverse the sign by multiplying it by a -1 essentially here, this is going to turn into a positive. If we want this to be a negative, this needs to be a smaller number than this is. This needs to be a smaller positive than this is a negative, so to speak, which means that T needs to be a small number. What benefits this more in proceeding forward? Which case of temperature, high or low, is more likely to make delta G be a negative? And the answer is low. A low temperature will make this term small, which means it doesn't outweigh this one, which means that delta G is a negative. As the temperature rises, there must be some point at which the temperature hits such a value that this term outweighs that term, and delta G goes from being a negative sign to a positive sign. I've rewritten the reaction here with the heat on the correct side. Now, some kids then start arguing, no, it's minus. You need to put a minus sign. No, minus in the delta H expression, that version tells me it's on the right side. So it is a product. The heat is, in a sense, a product, and it is plus this and that. The plus here just means and. The negative sign in the delta H value told me to put it on the right side. It's exothermic. So what would make this shift to the right? Well, I have 3 gas molecules and 2. And we know from our study of Le Chatelet's principle that squeezing this under higher pressure would favor the side with fewer molecules. Also, if I remove something on one side, the reaction will shift toward that side. And one of the products over here is heat. So if I cool the system, that also will mean that the system shifts to the right and tends to create more ammonia. There's also this equation, which we'll work with more later in the class, We said, remember, if temperature falls, delta G gets more negative. If delta G is getting more negative, then K here, and this is K equilibrium that we've worked with so many times, must be growing. And if K is growing, then the current set of circumstances that generates Q, remember Q is K math, but only at this exact moment, then Q must be smaller than K than normal because K is growing and Q hasn't been growing with it. If K is bigger than Q, then the reaction tends to proceed forward, which is just another way of proving the same point, that as lower temperatures, the reaction will want to proceed to the right. Now, not to do with this problem, but I want to point out that the Nobel Prize winning chemist Fritz Haber, and this is called the Haber process, uh, actually did a very clever thing. And what he did was he used high pressure, which tends to drive to the right, and high temperature, because that makes these bounce around really great, right? And run into each other with a lot of energy. So he has a lot of these with the activation energy. And that might seem like it's counterintuitive, but he also rigged a system where this doesn't build up. When this is generated, it keeps being drained out. So yes, the heat tends to drive it left, but when there is essentially no ammonia left in the system because it keeps getting removed, the system simply cannot go back left. There is nothing to go back left with. And I just thought that was an illustration of really understanding what you're dealing with in an engineering perspective.